Unit 3.1 is parallel lines and planes. The symbol for parallel is two vertical lines side by side. Parallel lines are coplanar, two lines that line the same plane. Coplanar lines that never intersect. This is an example of coplanar lines, and here's an example of the symbolism that we would use to say that one line is parallel to another line. When we look at this rectangular prism, and we want to make a little assumption that this is a rectangular prism, it's not as pretty as it could be. When we're talking about line AB, we want something parallel to it. It needs to be in the same plane. Well, if we think about the left side of the rectangular prism as being a plane, then we can see that in that plane, line AB and line CD do not intersect. So we could say that line AB is parallel to line CD. If we think about the top being a plane, then we can see that HE and AB do not intersect. So we could say that line AB is parallel to line HE as we think about those being in the same plane, the top, and never intersecting. Also, if we think about a diagonal plane that would run across that parallelogram, a diagonal plane that goes across, you can see that GF and AB are two lines that never intersect that are in that plane. So there's a third line we could say was parallel to line AB. In looking at lines that are parallel to BH, here's line BH. If we think about the front face of this rectangular prism being a plane, then we can see that CG and HB lie in that same plane and never intersect. So we could say that line GH and line CG are parallel lines. Thinking of the top again as a plane, we can see that line BH and line AE never intersect. So we could say that line BH is parallel to line AE, two coplanar lines that never intersect. And then thinking of DF as being in a plane that cuts diagonally across that rectangular prism, we can see that line DF is coplanar with BH and never intersects. And so we can say that line BH and line DF are also parallel. So parallel lines are coplanar lines that never intersect. The definition of skew lines is somewhat like parallel, except for instead of being coplanar, they are non-coplanar. So skew lines are non-coplanar lines that never intersect. If we go to the diagram and we look at line AB, we want a line not in the same plane as AB that never intersects it, and a line like that would be HG. There's not a plane that contains both of those lines, yet the two lines do not intersect. So we say that those are skew. So we say that line AB is skew to line HG. If we look at the other edge, vertical edge of the right face, we see that that's also skew to AB. They never intersect, but also they are not coplanar. And then it gives us line GC, and we want things to skew to that. So we want something not in the same plane, but never intersects, and one such example is EF. And another example is AD. Any questions on skew lines? If we think about a flat surface and a line that lies in that flat surface, and then we have another line that comes down and hits that at a point and then goes under, those are two lines that never intersect, yet they're not coplanar. So we can say that line L is skew to line M. Skew lines are non-coplanar lines that never intersect. Parallel planes. Now, when we think about a line in a plane, you can spin that line around and it's going to look a little bit different. But since planes go infinitely forever, if you tried to spin a plane, it really wouldn't look any different. We draw it as a parallelogram, but it's really not a parallelogram. It really extends without bound. So spinning the plane wouldn't make the plane look any different. So we're not going to have the term skew planes. We will only have the term parallel planes. And then all we need to know then is that they never intersect. So parallel planes are two planes that never intersect. If we look at the diagram and we talk about A, B, C, D, we're talking about the left face of the parallelogram, the rectangular prism, excuse me. And so parallel to the left face would be the right face of the parallelogram, which we could name parallelogram HEFG, or plane HEFG. If we think about plane ABHE, that would be the top. And the plane that would be parallel to the top would be the bottom. And the bottom was CDFG, plane CDFG. Parallel planes never intersect. When we think about a line parallel to a plane, since a plane goes infinitely forever without bound, then spinning it's not going to make it look any different. So there's only one visual relationship to a line and a plane. They either intersect or they do not intersect. If they do not intersect, we say they're parallel. So we say that a line is parallel to a plane if they never intersect. Visually, if we look at line AB, for it to be parallel to a plane, it needs to be parallel to a plane that's parallel to the plane that it lies in. The top is parallel to the bottom, therefore line AB is parallel to the bottom because it lies in the top, you see. And so we can say that line AB is parallel to plane CDFG. Now, BC, line BC, would have to be parallel to a plane that it never intersects. And the plane that it never intersects is going to be the right side of the rectangular prism, because BC is a part of the left side, which is parallel to the right side. And so it's parallel to HEFG. A line parallel to a plane. So parallel lines are coplanar lines that never intersect. Skew lines are non-coplanar lines that never intersect. Parallel planes never intersect. A line is parallel to a plane if they never intersect. Now we're going to get into a transversal and get into some special types of angles formed by two lines being intersected by a transversal, and then eventually get into some special characteristics of parallel lines and how to prove that two lines are parallel. So we're first of all going to start that journey with the definition of a transversal. A transversal is a line that intersects two or more coplanar lines in different points. A transversal is a line that intersects two or more coplanar lines in different points. We're going to look at some scenarios and decide whether the line in question is a transversal or not. Is L a transversal? Well, it intersects these two coplanar lines, but yet there's a problem. The problem is that it's supposed to intersect those two coplanar lines in different points. It intersects them in the same point, therefore L is not a transversal. In the next scenario, line T is the line in question. That might be some hint, since it has T as in transversal, that it might be the right one. But anyway, here's the two lines that it intersects. They are coplanar lines, and we notice also that it does intersect those two coplanar lines in different points. So yes, it is a transversal. It's a line that intersects two or more coplanar lines in different points. In the third example, the line in question as being a transversal or not is line L. We have this blue line that the red line, the line in question, does intercept at a point right here. And then we have this green line that's coming down, and it's actually passing underneath and coming out the other side. And it also intersects it down here below this plane. So that does intersect the two lines in different points. The problem is those two lines were not coplanar. So the problem here, they're not coplanar. The problem here, they did not hit in different points. These are coplanar. It did intersect each one in different points. Therefore, it fits the definition of a transversal. Any questions on transversal? Now, when we think about a transversal intersecting two coplanar lines, we visually can see 8 angles produced. Some of these angles are on the inside of the two lines. We call those interior angles. Some of those angles are on the exterior of the two lines. We call those exterior angles. And we will use those in making the formal definitions of alternate interior, same side interior, and corresponding angles. You may find a textbook there that would make alternate interior angles a definition, but I don't have alternate interior in this particular textbook. Now, the formal definition of alternate interior angles is two non-adjacent interior angles on opposite sides of the transversal. Two non-adjacent interior angles on opposite sides of the transversal. Now, when we make a geometry definition, it's a roadmap that tells us how to get what we're trying to get, or how to draw what we're trying to draw. So by a process of elimination here, we can figure out what a pair of alternate interior angles are. Now it says two non-adjacent interior. Let's just start out with the interior part. If they're interior, then that eliminates 1 and 2 and 7 and 8. They're eliminated because it said interior. Now, let's just begin with angle 3. That's an interior angle. Let's find the one that's alternate interior to it. So we're going to finish the rest of the definition. There's angle 3, a figure formed by two rays with a common endpoint, as you recall. It says two non-adjacent interior angles on opposite sides of the transversal. Well, here's angle 3, and it's got to be on opposite sides. Angle 5 is on the same side, and so that eliminates angle 5. And then it says non-adjacent. Non-adjacent. Adjacent angles are two angles in the same plane with a common vertex, a common side, and no common interior points, if you recall that definition. But what we thought about mentally is side by side. See, adjacent, side by side is the simpler definition that we put in our mind. When we go through that definition, it eliminates everything but angle 6. And so we can see that angle 3 and angle 6 are two non-adjacent, not side by side. Interior angles are both on the inside, on opposite sides of the transversal. Now, if you look at what is created as you draw angle 3 and 6 together, you'll see the letter Z. Now we want to know the formal definition, two non-adjacent interior angles on opposite sides of the transversal, but we also want to recognize they make the shape of the letter Z. Now that could be forwards or backwards or vertical or horizontal. It may even look like an N if you get vertical with it, you see. So those alternate interior angles would be like this, and there you can see the letter Z. Or they may be going the other way, this angle with this one. Those make the letter Z. Or your lines could be vertical, and so it may look like a Z that's been spun sideways. Okay? And so right here we're saying that angle 1 and angle 2 are vertical angles. Angle 3 and angle 4 are vertical angles. Angle 5 and angle 6 are vertical angles. Two non-adjacent interior angles on opposite sides of the transversal. When we get through with all that, we visually see the letter Z. Now we'll move to same side interior angles. Same side interior angles. Now, the formal definition is two angles on the inside on the same side. Okay, so let's draw two coplanar lines. Cut a transversal. Again, we have those 8 angles. It says on the inside, that eliminates 1 and 2 and 7 and 8. And on the same side, what's on the same side is angle 4, angle 6. On the inside, on the same side, and visually, we can see the letter C. Now that C may be forwards or backwards, or it may even be setting up. But we should be able to see in same side interior angles the letter C. Angle 1 and 2 here. Angle 3 and 4 here. Angle 5 and 6 here. Same side interior angles. Later, we're going to learn that if the lines are parallel, then alternate interior angles are equal and corresponding angles are equal, which we haven't talked about so far. These little arrows that I'm drawing would say that the lines are parallel. And then same side interior angles are supplementary. And so one thing that we say when we say that they're supplementary is same sides make a C and they're supplementary. That kind of helps us remember that. Same sides make a C and they're supplementary. A little jingle to help you remember that rule that's coming later once we get into parallel lines. So same side interior angles are two non-adjacent, same side interior angles are two interior angles on the same side of the transversal. And we can see that they make the letter C. The third special type of angles that we're going to talk about is corresponding angles. Corresponding angles are two angles in corresponding positions relative to the two lines. Excuse me, got a little carried away with the la-la-las there. Relative to the two lines. Two angles in corresponding positions relative to the two lines. So let's draw us two lines cut by transversal. Again, we'll mark out those 8 angles, 1, 2, 3, 4, 5, 6, 7, 8. Let's just think about angle 4. Now what we're thinking about here is the position that these angles have in relationship to the two lines. If we look at the intersection of the transversal and the top line, then there's 4 positions. There's the top left position, the top right position, the bottom left position, and the bottom right position. If we look at the intersection of the transversal and the bottom line, there's also 4 positions. The top right position, the top, the top left position, the top right position, the bottom left position, and the bottom right position. Corresponding angles, by formal definition, are two angles in corresponding positions relative to the two lines. So if we think about angle 4 as being the bottom right angle, then the one corresponding to it would be the other bottom right angle, which is angle 8. And if we draw angle 8 with angle 4, you see that they also make a letter, the letter F. Two angles in corresponding positions relative to the two lines. They're both in the bottom right position. That's the formal definition. Visually, we see that they make the letter F. It may be a forwards F or a backwards F or a sideways F. So here we can see that angle 1 and angle 2 are corresponding. Angle 2 and angle 4 are, angle 3 and angle 4 are corresponding. And here we see angle 5 is corresponding to angle 6. Two angles in corresponding positions relative to the two lines. And again, we see that they make the letter F. So alternate interior angles are two non-adjacent interior angles on opposite sides of the transversal. They make the letter Z. Same side interior angles are two angles on the inside on the same side. They make the letter C. Corresponding angles are two angles in corresponding positions relative to the two lines. They make the letter F. And so we're identifying more alternate interior angles, same side interior. Let's look at angle 3. Which one is alternate to angle 3? Well, we could draw angle 3. If we finish the Z, you see that it would be angle 6. Angle 3 and angle 6 are alternate interior. When we look at angle 4, if we start drawing it, we'll draw angle 4. Remember, it's a figure formed by two rays with a common endpoint. If we go down to the next vertex and try to make a Z-looking figure, you can see that angle 4 and angle 5 are alternate interior angles. Same side interior angles are two interior angles on the same side of the transversal. They actually make the letter C. So if we were to draw angle 3, if we get to the next vertex and try to make the letter C, you see that we would get angle 5. So angle 3 and 5 are same side interior angles. Angle 4, if we draw angle 4 and finish the C, we see that we have angle 6. Angle 4 and angle 6 are same side interior angles. Corresponding angles are two angles in corresponding positions relative to the two lines. Angle 1 is in the top left position of the top line and transversal. Angle 5 is in the top left position down there. If you connect them, you can see a letter F upside down, angle 1 and angle 5. Angle 3 is in the bottom right position. On the bottom line, angle 7 is in the bottom right position. If you connect those, you can see the letter F, angle 3 and angle 7. Angle 2 is in the top right position. In the top right position of the other line and transversals, angle 6. Again, if you connect those, you can see it makes an F again. Angle 2 and angle 6. And then the last pair, we have angle 4 in the bottom right position. Angle 8 is in the bottom right position of the bottom line, and if we connect them again, you see that corresponding angles make the letter F. Any questions on a transversal, alternate entry angles, corresponding angles, or same side interior angles? Okay. Theorem 3.1 says if two planes, now we're talking about these two planes, if two parallel planes are cut by a third plane, then the lines of intersection are parallel. If two parallel planes are cut by a third plane, then the lines of intersection are parallel. And we would show that these lines are parallel with little arrows inside the line. That's how you show parallelism within lines. Okay? Any questions on that? If two parallel planes are cut by a third plane, then the lines of intersection are parallel. Okay, that is the end of Unit 3.1 lesson.